Hello everyone. Today we'll be talking about algorithms, and I know that word can sound a little dry, but these are things that you're genuinely interacting with every single day. And so every Netflix recommendation, every GPS route, every scratch result or search result has an algorithm making that call. So let's get into it. An algorithm is basically a step-by-step procedure for solving a problem. And so if you've ever followed a recipe or made a pros and cons list, you've already been thinking algorithmically, probably, without realizing. And so what makes them powerful at a computer science level is that they let us apply the same structured logic to massive amounts of data, quickly and consistently, of course. They're basically the foundation of everything in the modern digital world, apps, AI, robotics, all that jazz. All right, moving on. And I want to really drive that point home. So algorithms aren't some abstract computer science concept. They're basically running constantly in the background of your everyday life. Every time you unlock your phone with your face, an algorithm is measuring distance between your facial landmarks in real time. When you open Google Maps and it routes you around traffic, that's an algorithm. Sorting your emails, also an algorithm. And so the entire digital world runs on this stuff. So when we talk about efficiency, this graph is really the key visual to understand. And so what we're looking at is time. How long an algorithm takes plotted against input size. And so a constant algorithm O of 1 stays flat no matter how big the problem gets. Linear O of n scales proportionally, but quadratic O of n squared, you can see that curve shoots up super incredibly fast. And so the difference between these isn't just academic. At, let's say, a billion data points, the gap between linear and quadratic is the difference between something that runs in seconds and something that runs for days. And so choosing the right algorithm matters very much. On to the next slide. Now, this is where we put some formal mathematics behind that intuition. And so what you're looking at on the screen is the asymptotic expansion of a recursive polynomial. And it looks like this. T of n is approximately the sum from I equals 1 to k of c of I times n raised to the power of alpha minus 1 times lambda to the power of n. And so let me break that down piece by piece because it's actually telling us something very concrete. So T of n is simply the runtime of our algorithm as a function of input size n. The summation is adding up multiple terms because most algorithms don't have just one growth behavior. They have several components, each contributing to the total runtime in different ways. Each term in that sum has three parts. The coefficient c of I is a constant that captures a specific characteristic of that component, things like how many operations happen per step. Then you have n raised to alpha minus 1, which is the polynomial part, which this is basically capturing the kind of growth we saw in the graph on the last slide. And so we have linear, quadratic, cubic, and so on. The alpha tells you the degree of that polynomial behavior. If alpha is 2, you're looking at linear growth in that component. If it's 3, quadratic, and so on. But here's the really interesting piece, which is lambda to the power of n. This is a exponential term, and this is where the connection to eigenvalue analysis from linear algebra comes in. And so when you solve a linear recurrence relation, which is exactly the kind of relationship that shows up when an algorithm calls itself recursively, the solution naturally takes this form, usually. And so the lambda values are literally the eigenvalues of the matrix representation of that recurrence. If any lambda is greater than 1, that term dominates everything else as n grows. Your algorithm becomes exponential. If all lambda values are less than or equal to 1, the polynomial terms take over and you're in a much better efficient shape. And so the practical takeaway here is that when you're analyzing a recursive algorithm, you're not just counting steps, you're basically solving an eigenvalue problem. And so the dominant eigenvalue of a system tells you the asymptotic runtime class. This is basically why computer scientists care so deeply about linear algebra. Moving on. And so here is a concrete example of where efficiency plays out in real life. Computers are searching through data millions of times per second. So even small improvements in search algorithms compound into massive gains. So you see on the left, you've got the simple methods, where you're just running through each data point one by one. It's easy to understand, but super slow as data grows. On the right is binary search, which works by cutting the problem in half every single step instead of checking every item one by one. And so it keeps dividing until it finds what it's looking for. And this is the kind of efficiency we're aiming for, and it's exactly the same thinking that powers our everyday applications. Moving on. And you can see it right here in apps I use every day. Netflix isn't just randomly guessing what you want to watch. It's running rankings and lookup algorithms against your viewing history in real time. Google is printing through billions of pages in milliseconds using layered indexing. And Spotify is basically doing the same thing to surface a song the instant you search for it. And so none of this is all wizardry or magic. It's all variations of binary search and smart indexing running at scale. And so these systems are fast because they are optimized, not because computers are infinitely powerful. And some problems, though, hit a wall no matter how clever your approach is. And these are called MP problems. And what makes them strange is that a computer can verify a correct answer almost instantly, but actually finding that answer is a completely different story. The search space grows so fast, it becomes computationally overwhelming, basically. It would run into these things in scheduling, cryptography, routing, which are some of the more or most important applied problems we have. On a side note, there is actually an interesting thread of research that draws a parallel between NP complexity and biological neural networks, things like calcium ion signaling and the combinatorial expansion of synaptic pathways. And so the argument is that graph structures of NP-complete problems actually resemble neural synchronization patterns in the brain. It's a speculative area, to be honest, but it's a reminder that the structures we study in computer science tend to show up in nature as well, which is pretty interesting, in my opinion. On to the next slide. A huge category of real problems comes down to one thing. Basically, given a bunch of options, what's the best one? And that's the optimization problem. Algorithms tackle this in different ways, and one of the most intuitive approaches is the greedy algorithm, which is exactly what we're about to look at. And so before we watch this video, I'll set the stage a little bit to explain what the greedy algorithm is. And so the greedy algorithm makes the locally optimal choice at every step. It always picks whatever looks best right now without worrying about what comes later. And so for example, let's say you're trying to make change. If someone owes you, let's say 68 cents, me personally, I would instinctively grab the biggest coin first. So I'll grab, let's say, 2 quarters, a dime, and then 3 pennies. And so this intuitive, always grab the best thing in front of you logic is exactly how the greedy algorithm operates. It's fast, it's simple, but for a surprisingly wide range of problems like network routing, scheduling, and resource allocation, they work surprisingly well. Okay, I'll let the video take it from here. All right, on to the next slide. So this equation down here that you see, psi of x equals the sum of alpha times e to the power of I theta, is a quantum wave function. And so in quantum mechanics, a particle doesn't exist in one single state. It exists in many possible states at the same time. And this equation is expressing that mathematically. Each term in the sum is a wave oscillating at a different frequency, and the alpha coefficients tell you the probability of landing on any particular state when you actually measure the system. And the reason this shows up here is that some researchers think decision-making works similarly. Instead of having one fixed preference, your brain might hold multiple weighted options simultaneously. And the act of making a choice in the moment, or the act of making a choice is the moment it all collapses into one answer. And so some preferences reinforce each other, some cancel out, just like waves. It's still a pretty theoretical area, but the math turns out to be surprisingly useful um, for how people make choices under uncertainty. All right, so I'll bring it all together. We started with what algorithms are at their core, talked about how we measure efficiency formally and visually. We saw how recursive polynomial expansions and eigenvalue analysis gives us precise tools to classify algorithmic complexity and watch that play out in real-world search and sorting. We looked at where problems become genuinely hard with NP complexity, and closed out by seeing how quantum wave function mathematics offers a fascinating model for decision making under uncertainty. And so the through line in all of it is that algorithms aren't just a coding concept, they're a way of structuring thought. And the better you understand them, the sharper your problem solving gets, across the board. Thank you, everyone, and I am happy to take questions.